Here we will construct the forward kinematics for a number of the robots that are contained in our industrial robots section. The first robot we have is this Denso brand Scara robot. The Scara is a 4-axis robot for pick and place. See some you can see a picture of it here. Some various side views. And here we have, well, here we have a nice side view, if you will. Here we have a top view. This shows the workable space for this robot. This is the base of the robot. You can see a top view of the 2 arms. We have a Revolute here. In the Scara, of course, we have a Revolute, and Prismatic. Actually, I'd say Prismatic and the Revolute. So we'll call it an RRPR robot. Here's some of the specs on this arm. First, we'll do the frame assignments. We'll go through our steps. We'll identify the joints. This is joint 1. This is joint 2. This Prismatic here we'll call joint 3. I'm going to call it P to note this is Prismatic. And then, of course, joint 4. We'll be back to our Revolute. We need to assign the, next we assign the Z-axis. We'll put Z0 along joint 1. I'll put Z1 along joint 2. Z2 is going to go along joint 3, the Prismatic. I think of the Prismatic in the normal direction going down, so I'm going to run Z2 down. Z3 is also going to come down. I'll line up Z3 with Z2, and then finally Z4 is my last frame. I'll put it out at the workspace of the robot. Now, I have not identified where the origins of these frames are, but I've kind of done it, you can see, with my frames, but this is to be termed from the X's. Now I define the X's. My first X is free to assign. That's X0. I assign frame 0 arbitrarily, X0 here. Now I'm probably going to switch that around because it looks like it normally works out in this space. So call it X0. X1 is perpendicular to Z0 and Z1 and intersects both. I've got an infinite number of these to choose, so I'm going to choose the one that intersects along this line, so I'll call that X1. Same with X2, which is the common normal between Z1 and Z2. So I'll put X2 out here. Then I have X3. X3 will also be perpendicular to X2 and X3. So you can't see it here, but X3 will rotate relative to X2. It could. And then finally down here, I'll get X4. I'll put it down at the base. So there I've got my 4 frames. Well, actually 5 frames starting with 0, but I end up with frame 4. Now I have to define the D and H table. Put the D and H table right here. Try to put it in close. So I'm going to define joint I. For joint I, I'll have A sub I, alpha sub I, D sub I, theta sub I. Don't need all that room. And my joints are joints 1, 2, 3, and 4. So I have 4 rows in this table. I'll start out with the A's. A's are the distances between my Z's. So A1 is the distance between Z0 and Z1. So you can see from the picture that's B. A2 is the distance between Z1 and Z2. You can see from the drawing that's 225. A3 is the distance from Z2 to Z3. They intersect. Z3 and Z4, they intersect as well. Next, I have alpha is the angles between my joints. So Z0 aligns with Z1. Z1 to Z2 is a 180-degree rotation around X2. Doing my right-hand rule there. Frame 3, 2 to 3, they're in the same direction. 3 to 4 are also in the same direction. Next, I have my D's, the distance from Z0 to Z1, excuse me, X0 to X1, measure along Z0. I think I wanted to line it up with this guy right here, so I can call that 566. distance from x1 to x2. I decided to make those intersect. So on the same line, so it'll be 0. Distance from x2 to x3. Yeah, I probably should have shown that one in the picture. I think I'll go back and do that. That will be the current displacement of the arm. So I'll run it somewhere down here. So I'll just call that D3, put a star next to it because that's my joint displacement. And then finally, distance from x3 to x4. Notice they've got this 312. I haven't defined a specific offset. I'm guessing this 312 is showing a maximum displacement for this guy. I don't have a good number that I could pull out from that, so I'm going to have to just define it here. Be nice if they gave me the height of that little bar, because I'm assuming that's the minimum that it can withdraw, but we'll just call that D4. And I'll put in my notes as D4. Finally, I need the joint angles, so theta 1 is my first joint variable, theta 2 is my second joint variable. Theta 3, that's a constant, right, because that's with this prismatic, and I assume that x2 and x3 are in the same direction, so I'll get a 0. And finally, x4, or theta 4, my last joint variable. So that gives me my 4 joints. And recall that each row will give me my corresponding transformations. And I'll build those up appropriately and install them. Okay, next, let's move to our next robot. Our next robot is this, again, Denso Robotics. I like Denso. They have a large automotive division, of course, in the States, in Tennessee. And they have a series of robots here. So here we've got their VSG series. I've got a picture of it here. You can see it's an articulated configuration. I can see that because I have the 3 revolute perpendicular. It's a R perpendicular to an R, parallel to a third R. That's the articulated. And it's got this spherical roll, pitch, roll, wrist. So we can call it a roll, pitch, roll, wrist. If you will, that's how we would refer to this robot. And I have a side view here showing workspace of the robot, and you can see dimensions correspondingly. We'll construct our frame assignment on this drawing here, on this 2-dimensional drawing, the side view. My first I have to define the joints, so I can see that there's a revolute joint about the base. I'll call that J1. Then I have a joint here, J2. I have similarly a joint here. Well, actually, they're labeled on the picture. You might not be able to see. I think I can zoom in a little for this portion. So I can see J2, J3. Let's see. I don't really show J4 on this drawing. So J4 would be this guy. You can see J5. And then finally, J6 is that final roll about here. Okay. Next, we can assign frames. Well, I say assign frames. The next step is to assign the Z's. So I have Z0 along joint 1, Z1 along joint 2, oops, Z2 along joint 3, Z3 along joint 4, Z4 along joint 5, and then finally, well, not quite finally, right, because we're going to 6, but Z5 along joint 6, and I will label them as follows, Z5 and Z6 out here. Next, I need to find my X0 I'll just run that horizontal the way I normally do. X1 is orthogonal between Z0 and Z1, so take my right hand, point in the direction of Z0, curl it towards Z1. Z1's coming out at me, so fingers up, curling it out toward me. So it gives my thumb pointing back that way is the positive Z1 axis. I think I'm going to choose to point it this way. If I'm saying Z, I meant X. So I'll put X1 along there. Z1 and Z2 are parallel, so I need a parallel line between them. I'll keep that in line, so I'll call that my X2. Okay, now Z2, there you go. Stop it here. That's my X2. Z2 is coming out at me. Z3 is going that way, so Z2 coming out toward me. Z3 going forward, so I get Z2 cross Z3. That puts X3 going down. I'm going to choose X3, though, going in the opposite way. I'll put a little negative here temporarily to remind me that I chose those two in the negatives. It'll help me out when I do the frame assignments, or table. Z3 cross Z4, those are also orthogonal, so I've got Z3 going this way, Z4 coming out. So I'll put X4 going up. I have Z5 going forward, so I've got Z5 coming out, or Z4 coming out at me, Z5 going that way, so I've got X5 going down. So I'll choose also X5 going up. That gives me another negative, so I've chosen 3 of these in the negative direction just to keep things lined up. And then finally Z5 and Z6 are in the same direction, so I can put X6 wherever I want, and I'm going to put X6 right out here at the face of this arm, so that'll be the beginning of the end effector. Here we go, X6. Now if I had a tool on that end effector, I could, if I wanted, I could put that frame out with the tool. So, and that practically, if you're working with robot systems in your job, that's probably where you're going to interface. Okay, now I need to move to the next step, which is I've got my frames assigned. Now I'm going to choose my D&H table. Put it up here. This guy's going to have 6 rows. So I'll define I, A sub I, alpha sub I, D sub I, theta sub I. Maybe need these 5 columns, and I need 6 rows for 1, 2, 3, 4, 5, and 6 joints. As follows. I'll go 1 column at a time. So I'll start with A sub I. That's the distance between my Z's. So the first thing I have is distance between Z0 and Z1. That's A1. Oops. Let's pause for a second. I want to turn on these lights in here. So A sub 1. Hopefully you can fast forward through this. Is the distance from Z0 to Z1. I can see it's 75. A sub 2 is the distance from Z1 to Z2 measured along X2. I can see that that's 270. These, I'm sure, are in millimeters. A sub 3, distance from Z2, which is coming out, Z3 up here, I can see that's 90. A4, distance from Z3 to Z4, they intersect. A5, distance from Z4 to Z5, they intersect. Z5 to Z6, they also intersect. It's a spherical wrist, hence they all intersect. That's what I guess zeros mean here. Alpha sub 1, the angle between Z0 and Z1, measured about Z0, so that's negative 90. I have my little notation there to remind me of that. Angle from Z1 to Z2, those are 0. Z2 to Z3, that's also a negative 90. I went the opposite way. Z3 to Z4, that's a positive 90. Z4 to Z5, again, I chose the negative direction, negative 90. Z5 to Z6, that's 0. Next, I have my D sub I, the distance from between the x's. So from x0 to x1 measured along z0 is this 335. Distance from x1 to x2, they intersect. Distance from x2 to x3, those guys also intersect. Now I can't quite see that without doing a side view or a back side view. So if that's this guy here, and if this were this guy, this joint, where I have my z's going this way, I have chosen my, I guess then if I go on the side, I guess my x1 goes back, my x2 is going up. Do you see this idea? So they intersect. I've chosen them to intersect. Not the best line in the world, but I've chosen those to intersect. And then with this drawing, if I move up a little more, this axis here, I will have my Z3 going this way. And then X3 is also, so my Z2 crossed with Z3. Yeah, what do I mean? My X3 going down, but I went in the opposite direction. So that's my X3 going up. So I can see here pretty clearly that X1 to X2, the distance is 0. X2 to X3, the distance is 0. From X3 to X4, though, along Z3, I can see I've got 295 for a distance. X4 to X5, those guys intersect. Right there at that wrist. And X5 to X6, I've got that little offset 80, marked as 80. And then my last column, these are all the joint variables. In this case, this is fully a Revolute robot, so it's theta 3, stars next to all these. Oops. And again, I'll get my transformations. And to get my total transformation, I'll build each one up, multiply, and that will give me my final Ford kinematics. Here's another view of the robot, a top view. You could have also done some frame assignments on this guy. Okay. Let's go to our next robot. Next we have this Fanuc, one of the leaders in robotics, a long-known name. One of their major integrators is Lincoln, and they make probably the largest percentage of welding robots, perhaps, at least they're sold in the States. They interface directly with Lincoln. As you can see here, they've got a wire feed, the torch passing up through the arm very cleanly. This is one of their welding robots. They probably have at least 10 or more in their line. This is the, I didn't label it. Oh. This is their, I think it's like their 100 CI L something series, maybe L7 series. I'm not sure. It's their 100C. It's their 100CI series, though. Or 100I series, I guess I should say. They have A's and B's and C's. Maybe the C is their third vision of this. I guess I forgot to write that down. Anyhow, we need to do frame assignments for this guy. I'm going to work off this table below, this picture below here. Zoom in a little bit. So I can see my joints. Joint 0 going up, joint 1 right here, joint 2, joint 3, excuse me, joint 1, 2, 3, 4 along here, 5 about this guy, and 6. So it's that roll, pitch, roll, wrist again. Frankly, it's the same exact configuration that we saw. I say configuration topology with corresponding offsets. So we should get the same idea. So I've got a Z0 coming up. I'll call a Z1 coming out of the board, a Z2 coming out of the board, a Z3 going off this way, Next I have a Z4 there, a Z5, and finally a Z6 coming out that way. To define my X's, I'm going to put my X0 here. I've got Z0 going up, cross with Z1 coming out at me, so that I'll put X1 out here, that intersects both. Z1 cross Z2, they're parallel, so that I can put my X2 up here. Z2, because I shouldn't get so carried away. Z2 crossed with Z3 puts my X3 going up. So now notice, kind of like before, I've got all these orthogonal guys, but now everybody's showing up in the positive direction just because of the direction I assigned the Z's. Z3 to Z4, oh, I see I labeled that wrong. Z3 going to the left, or my right, crosses Z4 coming out, puts my X down. So I'm going to run my X up. That's my X4. That one is first one negative. Z4 is coming out, cross Z5 going forward. So that'll give me my X5. And then 5 and 6, they're collinear. So I'm going to define X6 up here. That'll be a rotation. There's my frames. Also, same as before, this side view doesn't really show displacement out of plane, but I'm going to assume that everything is in plane for that. Okay, I'm not going to draw that graphic, but I'm making that assumption. So when I do the D&H table, which I'll do here now, okay, my I is 1, 2, 3, 4, 5, 6. I have my A sub I, my alpha sub I, my D sub I, my theta sub I, corresponding directions. We'll start with, see if I can clean that up a little bit. We'll start with A's, distances. So the distance between Z0 and Z1. Not shown on this picture, is it? Not shown on this picture. I guess I should, be nice if it were, so I'm gonna have to sketch them in. But nice if I would grab a dimension drawing. I didn't though, so we'll call that A1. Distance from Z1 to Z2. That'll be our A2 here. Z2 to Z3. That'll be this distance. Z3 to Z4, they intersect. 4 to 5 intersect. 5 to 6 intersect. So I get A1, A2, A3, 0, 0, 0, where A1, A2, A3 are shown on this drawing, and A1, A2, A3 will come from the specs for this robot. Next, I do my alphas, the angles between Z0 and Z1. There's a positive 90, Z1 to Z2, they're parallel. Z2 to Z3, that also chose a positive 90. Z3 to Z4, that was our first negative 90 choice. 4 to 5, positive 90, and then finally 5 to 6 are parallel. Okay, distances. Distance from X0 to X1, measured along Z0. Well, that would be this guy, D1. X1 to X2, we're assuming that those are in line. 2 to 3 in line. 3 to 4, that would be this distance. We'll call it D4. X4 to X5, they're in line. X5 to X6, call that D6. So I get a D1, 0, 0, D4, 0, D6. And then finally, this guy is all revolute joints. And correspondingly, I'll get my intermediate transformations from T10 to T65, do my multiplications, and that gives me my fluid kinematics. Next, I'm presented with my first collaborative arm. The collaborative arms are a new wave in manufacturing. They're very slowly hitting the, as we speak, they're very slowly starting to come into use in industry. I think now at this point I was just at a show, and I think most major manufacturers have one or more collaborative arms in place. The one that I work with closely is this guy. It's made by the company Obo. Their home is Knoxville, Tennessee. So, and my collaboration with this company. And you can see their i5 given here. The i5 is a 5 kilogram arm, and it's once again an articulated configuration. So this is the Oboe i5. It's an articulated configuration, and it has a non-spherical wrist. So we'll see in just a moment. The wrist joints do not intersect. So it's non-spherical. Remember we said that spherical wrists are required to get closed form solutions of the kinematics. So this guy does not have closed form solutions to kinematics to the best of my knowledge. All right, here we have the arm standing straight up in its home position. They call this the home position. So let's apply the frame assignments here. You can see the joints, revolute, 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 as follows. So let's start out with frame 0. I'm going to zoom in a little bit. A little easier to see. And I'm going to change colors. Let's go to a nice shade of red. Whoa, I don't like that. Let's try a nice shade of blue. That's better. Z0. Okay, so we had joint 1 coming up. Joint 2 goes across like this. So I'm going to put Z2 going this way. Now recall they intersect. So since they intersect, I say recall, but you can see they intersect. So I better put Z1 back here. I don't know the origin yet, but I'm kind of alluding to it. Let's see, Z2 to Z3. I can frame, excuse me, I got sidetracked. Joint 2, joint 3 is a revolute here. So I was thinking out loud, so I'm going to put my Z3 somewhere along this guy. I don't know the origin yet. I say Z3, I mean Z2. That's along joint 3. I guess I just need to take the time to label these. So I got a joint 4, joint 5, and a joint 6. So we've got Z3 along, or Z2 along joint 3. Now we need a Z3 along joint 4. I need a Z4 along joint 5. I need a Z5 along joint 6. And then I need a Z6 out of my end effector. Don't forget, you always have to end with the N, Zn, where N is the degrees of freedom of the robot. That's why in the Spelling notation we start with 0. Now we go to the X0. X0 I'm going to define arbitrarily horizontal. X1 is the common normal between Z0 and Z1. So Z0 is up, Z1 is this way, so I get X1 right there, no choice. There's my X1. Z1 cross Z2. Well, I can put that anywhere. I can keep it in line. You know what I'm going to do? I'm actually going to choose to put it in line with this guy out here. So I'm going to put it right here. That's my X2. This is weird. The lights just turned off. Hold on, I'm going to go. With my hands. Let's see, I just did X2. Z2 to Z3 is going to be my X3. So he's here. X3 to X4. Now those guys are not, those are orthogonal. So we got Z3 cross Z4 going up. Thumb into the board will be the positive direction. I think I'm going to choose that one coming out. So I'll make that guy my X4. And I'm going to put my little negative here to remind me. Z4 to Z5, they intersect up here, coming out of the board. So it'll be my X5. And then finally, Z5 to Z6, they're parallel. So I'll put my X5 right here, or excuse me, my X6 here. And that was my Z5. Okay, there's my frame assignment. I'm going to zoom back out and draw in my transformation matrix, or excuse me, my D&H table. So I've got my columns A sub I, alpha sub I, D sub I. Oops, I got my alpha, didn't I? Alpha sub I, D sub I, theta sub I. Get 1, 2, 3, 4, 5. Need 6. Now I'll go through my joints. So first I have the distance from Z0 to Z1. They intersect Z1 to Z2. You can see that they're parallel here. So that'll give me my L. We'll call that L2. Z2 to Z3. Call that L3. Z3 to Z4, they intersect. Z4 to Z5, they intersect. Z5 to Z6, they all intersect. So I just get an L2 and an L3, 0, 0, 0. Next, I have my alpha sub I. That's the angle Z0 to Z1. That was 90. Positive Z1 to Z2 was 0. 2 to 3 was 0. 3 to 4 was 90, but we chose the negative direction, so I get negative 90. 4 to 5, positive 90. 5 to 6, they're parallel, so that's actually collinear, 0. D1 to D2. Excuse me. X0 to X1, that's my D1. So we had that little offset there at the base. X1, which is coming out of the board, X2 is going up. So that's my D2. D2 or X2 to X3, I chose those that intersect. X3 to X4, they intersect. X4 to X5. Let's put those two down. X4 to X5. X4 is coming out of the board. X5 is coming out of the board. But they've got this little offset between them, so I'm going to call that my D5. And then X5 to X6, those are also coming out of the board. I get a little offset here, D6. And then finally, this robot is fully all revolutes. So define my joint axes, and then I'll create my transformations from top to bottom and multiply, and that gives me my frame, my D&H. Oops. I'll complete my forward kinematics. Okay, moving along. An Adept Viper. Well, this is made by Adept, another historically very famous company in robotics. I can see that this is an articulated configuration. Get a revolute, 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 revolute along there, revolute here, and then revolute along here. And that's the same configuration that we've already done twice, so we're going to move past it. I get a Fanuc robot, P for painting. This is one of their P series robots, one of their paint robots. They have a whole line of painting robots. And maybe we'll go ahead and try this guy. This one looks just a tad bit different. Okay, so let's try it. The painting arms, maybe slightly less resolution, longer reach, all sealed up to keep the thing clean. They're wanting to paint in a very clean environment for high-end painting operations. So if we look at our joints, we got a joint 1 here, joint 2 there, joint 3 here, joint 4 there. Now this guy is going to seem strange. There's a revolute joint right here, so it runs this way. Joint 5, and then finally a joint down here, 6. So this guy is not a spherical wrist robot. We'll assign the rest of our, we'll complete our frames, so we've got now the Z's. So I get Z0 along joint 1, Z1 along joint 2, Z2 along joint 3, Z3 along joint 4, Z4 along joint 5, Z5 along joint 6, and then Z6 also. I'm going to make it parallel to Z5, get my X0 here, Z0 across Z1 coming out of the board, then I'll put my X1 here, Z1, Z2 are parallel, so I'll put my X2 here, it intersects both, perpendicular both. Z2 to Z3, I cross those, I use my right hand to do that, it gives me an X3 up here. Z3 cross Z4, Z3 cross Z4, that puts my X4 here, Z4 cross Z5. Oh, you know what? Hold on. So I did that wrong. Not sure what I was doing. I was pretty convincing though, I'm sure. I messed up. Z3 is coming out. Z3. Z4 is going down. So I got to be perpendicular to both. So that's going to put it into the board right there. I'm going to choose out of the board. So I'll call that X4, and I get my little negative up there. Z4 across Z5. Z4 is going kind of down at an angle. Z5 is coming up this way, so I'll put my X5 right here. It's coming out of the board. And then Z5 cross Z6, and I'll put it out of the board as well. Right there, X6. Pretty tight. Wish I had a little more room, but that'll work. Now I have to do my D and H table. So I get my I, my A sub I, my alpha sub I, D sub I, theta sub I, rows 1, 2, 3, 4, and 5, 6 below it. Columns. Not exactly the best lines in the world. I have 6 joints, so I need to write those down. Now, A sub I, distance from Z0 to Z1, they intersect. Z1 to Z2, I get this L1 here, or we'll call it L2. Z2 to Z3, they intersect. Z3 to Z4, they intersect. Z4 to Z5, they intersect. Z5 to Z6, they intersect. So everything here intersects with my Z's, but that doesn't necessarily mean my 4 intersects 5, 5 intersects 6, but these are not necessarily the same direction. So, excuse me, same position. So this is not a spherical wrist. Next, I need my alphas. So Z0 to Z1 is a positive 90. 1 to 2, they're parallel. 2 to 3, that was a positive 90. 3 to 4, I chose my negative 90 for that. No, not negative 90. So it was Z3 cross Z4. So it was this angle here. Not sure if that's a 45. It looks like a 60. I'm going to call it a 60. I'm not sure what it is. Z4 to 5. Oh, and I chose a negative for that. And then I went back positive 60. I'm going to put a little symbol up here. It's 60 or your value. And then finally, these guys were collinear. Now the D's. Distance from X0 to X1. That is D1. X1 to X2. I'm assuming they're intersecting. I'm not showing that side view, the view looking from here, but I've just assumed I'm going to line them all up. So that makes X2 to X1 to X2, 0, X2 to X3, 0, X3 to X4, get carried away, X3 to X4, which is here. So I need a D4 running along there. X4 to X5, that's that very tight space right here. D5, X5 to X6. Very little offset down here. I'll call that my D6. So the fact that I've got these offsets here imply that I'm going to have a, I think, now that I think about it, to be spherical, these three have to be 0 and this guy has to be 0. That's the requirement for a spherical wrist. And since this guy is not spherical, I guess it's not a spherical wrist. Finally, I get my joint values. And these were all my joint variables, so I'll identify them appropriately. Okay. How many more robots do we have? Fanuc M401B. I think this is one of their pallet pick and place moves, and you can see that they have these 4-bar linkages. Effectively, this is going to act as a parallelogram. It does two things, actually. It moves the actuator for this joint, gets driven all the way down to here. The actual, which you can see right there. The actuator for this joint gets driven back on this bar right here. So there's going to be three. There should be 3 actuators, one here, 2 that's driving that arm, and then somewhere, I can't quite see it, a third one driving this other wrist. That then leaves you with a joint here and a motor for that guy. So it makes the, oh, I see. You know what? Here's the other actuator right here. It's this big linear guy that's driving the thing up and down. So it's fairly interesting, intriguing design. However, for the purposes of our robot frame assignment, we're treating serial link mechanisms only. So in our analysis, we're not really treating these extra imparallel links. So we have a revolute coming up, a revolute coming out here, a revolute coming out here, a revolute coming out here, and then a revolute coming out here. So this is a 5, that's joint 5, 5 axes, and you would treat it in the normal way. Or 4. Maybe they're not even referring to joint 5, actually. Just for what it's worth, you can see why this robot is being made. 410/450 has a 450 kilogram payload. That is about 1,000 pounds. So this robot could easily pick up car frames and move them around, and that's its purpose. Repeatability is 0.5 millimeter, 1,000 pounds at 0.5 millimeter. That's pretty impressive. Here's the Adept Viper. Looks just S650. This is a 650 millimeter reach, hence the name S650. It's just like the Adept. What did we just see? Oh. Looks like it's a copy. Same one. My notes are bad. And here we have the Adept Cobra. This is an old robot here. Old. But, I guess still very functional. It's the Scara. We talked about, they call it their I600. Actually, I don't know how old this is. It looks old. Okay, this is new, the Adept Quattro. Now Fanuc has a Quattro. This is a in parallel mechanism. This guy has 4 serial chains that start here and go all the way down to the base. So this is an in parallel mechanism. You can see these 4 chains. See how lightweight these arms are? All the motors are up here. This guy can do X, Y, Z motion, and then some of them have there's four 4 arms are just going to give you 4 degrees of freedom. So this is a 4-DOF arm. I'm assuming this does X, Y, Z in rotation. So this would replace a SCARA. It would be the same motions as a SCARA. But the methods that we learned in class do not cover parallel architecture robots. So there's really nothing we can do with this other than observe it and be impressed. Look at the payload, and then what's very impressive is the speed. So you'd have to go watch one to see. Finally, we have the KUKA. I think this is the last one on my list. I have a KUKA 33. KUKA is another very popular brand of robots. And you can see the 33. This guy's a 30-kilogram payload, 2,000 millimeter. Oh, excuse me. So it's a long arm. And I've got a joint 1 is down here. Joint 2 comes out there. Joint 3 comes out here. Joint 4 is slightly above it. Joint 5 right here. And then joint 6 out of the end effector. So it is the same articulated configuration that we've seen many times. All the manufacturers, it seems, make this particular configuration. It's just darn handy, I suppose. Sometimes you see an offset here, and sometimes you don't. We've seen examples of both so far today. Okay, with that, we will conclude this demonstration.